Good afternoon, Professor.
Good afternoon, Carolyn.
Good afternoon, Professor.
Good afternoon, Savannah. Good afternoon,
Good
Savannah.
afternoon, Professor.
Good afternoon, Stephen. Good afternoon, folks. You guys are so, especially in these trying times, such a pleasure. And I don't know, but I'm serious. It's like become a new contest for me whether I can catch. I always catch Caroline's green square, but I never catch Savannah's green square. And I think it's like the universe is. There's something about anyway. Wait, someone is here. Okay. I know it's okay. Good afternoon, Amanda. Good afternoon, Caitlin. Good afternoon, Amy. Good afternoon, Don. Good afternoon, Mackenzie. Good afternoon, Erica. Good afternoon, Kevin. Good afternoon, Sumaya. Wait, there's more. Good afternoon, Jose. Okay. Yes, thank you for your indulgence and patience as always, all of you. I'm going to try to make this quick. I know I was out on Monday. I was also out yesterday. I wasn't on campus yesterday. And I missed seeing some of you that I like to see on Tuesdays, and I will be back on Tuesday. And I'm sorry if you came looking for me. And I'm sorry that I've been out. Everything is fine. Stuff I'm happy to explain to anybody who wants to know outside of class. Hold on. But the bigger thing that I'm apologizing for, of course, I'm very aware that most of you have not gotten your exams back yet. Wait, I'm just fixing the board. You saw the announcement in Google Classroom, no doubt. I won't dwell on it all period. I don't want to waste more of your time, but they've started to come back finally. My machine, was very behind and moving very slow, but now it's starting to pick up speed. So you're starting to get them back. I'm doing the same thing I think I did last semester, I've done before, where you just get, as soon as I finish one, you just get it back. I'm not waiting for all of them to be done. So most of you have not gotten them back, and they're coming back in random order. It doesn't mean anything if you have gotten it or haven't gotten it. It does mean that finally they're in progress, and you should be getting them in the next few, by the end of the week. I truly apologize. And again, I don't want to spend all period talking about it. Obviously, there's not anything I can do about it during this period. But just to be clear again, what was in the classroom, you don't have to do any new work ever until the final exam. And I know that it's very difficult to think about a final exam or do anything until you have these results. I know that. I'm sympathetic to that. And I try to make as many accommodations as I can when I do all your final numbers and everything. One thing for example, I didn't put this in classroom. Hold on, let me just fix the board. But one thing that I think I did do last semester, I frequently do, especially under these circumstances. I think I did it for you guys last semester, but that is this, that no matter what, I know we're done with the bulk of the semester. I know we have very little time left in the semester. And I know the amount of time you'll have to be able to use your results from your midterm to help yourself practice and prepare for the final, I know is getting shorter. I'm very aware of all those challenges that I'm unwittingly imposing on you. So just to be clear, the final exam will not be as long as the midterm. The midterm was like the big hump for everybody to get through. The final exam won't be as long. It won't be as much material. And as I think I did last semester, the final exam is meant as an opportunity for those of you who are still concerned about your grade by the time you get there to do better. And those, when you finally get back your midterms, if you got a grade on it that you're comfortable with or that you're confident with, you won't be able to damage yourself that badly with the final exam. In other words, I'm going to do the same thing as I've done in the past, which is whichever of the two exams you do better on, I will count more. I can't ignore either one of them. I can't throw out either one because you only have two, but I will put more weight on whichever one you do better on. So if you need the final exam as a chance to rectify things, then that's what it will be. But if you get my point. If you've made things solid with yourself with the midterm by the time you get it back, then you should be able to not have to stress as hard about the final. It's the best thing I can say under the circumstances. Just also know, once again, my goal is for you guys to do well. It's not to make your life any more difficult than it already is. So I fully recognize that the longer I take with these exams, the more compassion and understanding has to be built into final outcomes for all of you. Believe me, I get that. I hope you get what I'm saying. I'm just making them. So if there are any more questions on that, of course, you can put in the chat, or you can email me privately or text. But just again, you'll be getting, each one of you will get your exam fairly soon. They're just coming one at a time. And I apologize. Okay. So now I'm going to go. So the other thing is, like I said, there's no new homework at all. The last homework that was ever assigned was this electric field one. I think technically it may have been due today or something, and I know about half of you have turned it in. What I'm going to do today, right now, and one of you asked me this in an email, actually, what I'm going to go over the second part. I'm going to walk through the second part of it right now. So if you have done it already, that's great, and you got a big leg up on it. But if you find out that you did something wrong or incomplete or something from what I'm about to do, you, of course, can upload and fix it. And if you haven't done it yet, hopefully this will help you. Either way, this problem that I'm about to go over now usually is one of the problems on the final exam. Like it usually is. So hopefully I'm not wasting your time by going over this. It's heavy computation problem, but once you get used to it, hopefully it's not a crazy computation. Okay, so this is what I'm talking about. I'm just doing the board. Okay, I'm talking about this. I'm talking about that again, the most recent homework. And again, please stop me with any concerns or anything in the chat. The best thing I can say is we're all just trying to catch up. I mean, you shouldn't have to be doing anything new. You should just be trying to catch up to me, and I'm trying to catch up to you for the remainder of time we have. So the assignment, well, I think it was homework 6. It's called From G to E Fields, and it's part B that we're talking about now. And the setup for part B can be understood in this diagram right here on the book. Excuse me, hold on. This diagram here is meant to depict that you have a coordinate plane, you have a two-dimensional region of space, and in that region of space, you have 2 point charges. You sitting in the space, you have 2 point charges. One is a positive charge, the other is a negative charge. They are point charges, meaning like the positive one that we're calling Q1. What does that really mean physically? It means there's a whole bunch of protons jammed together in a really tiny, perhaps infinitesimal volume of space. Enough protons to equal up to 5 coulombs of positive charge magnitude. Now it happens that the charge of one proton is approximately 1.60 times 10 to the negative 19th coulombs. Okay, a coulomb is actually a very enormous amount of charge. It's an amount of charge that starts to be big enough that it really have a measurable effect on macroscopic phenomena. The charge comes from these microscopic particles known as protons and electrons. So it does take a huge number of protons to make a coulomb. There's approximately 16 quintillion protons to constitute 1 coulomb. So when we say that we have a positive 5 coulomb point charge, again, what we're imagining or what we're considering, trying to picture in our mind, is this vast number of protons all jammed together in a tiny space. Now, and that is actually realistic. These are sort of, well, 5 coulombs is a lot of charge, but it's a plausible amount of charge. These are, in other words, actual vaguely realistic numbers. The whole thing is hard to picture on the one hand because protons are so small, and on the other hand because we're asking you to picture so many of them in a small space. So it's hard to picture, but that's just it. It's just hard to picture because of the sizes involved. The concepts involved here are all the same concepts as the concepts and the math involved in whatever happens when you have like a planet of mass over here and maybe a moon of mass over there, or a star of a lot of mass over here and a planet of mass over there, or even better yet, a point of mass and another point of mass. Like the concepts of the way protons and electrons interact with each other through empty space is the same concept and the same mathematical relation as the interaction between points of mass in space, for whatever it's worth. So here we're dealing with electricity. So you've got, in this given situation, you've got, so we've got a positive 5 Coulomb point charge, known as Q1, sitting at coordinates positive 5, positive 4. Then you've got this other point charge. This one's negative. It has a value of negative 2 coulombs, and it's over there at coordinates 10, 3. So again, in short, up here you have this enormous number of protons, maybe actually 80 quintillion protons jammed together in a tiny space up here. And then over here, you've got a bunch of electrons. Maybe you got 32 quintillion electrons jammed together in a tiny space over here. And our ultimate question of this problem, our ultimate quantitative question is, what is the electrostatic field created at, for example, the location 0, 0, due to these 2 point sources of charge? Okay, so the question is written here on the board. Excuse me, I'm just going to change the view of the screen. Pardon me for a second. Okay. The question is, at the point 0, 0, what is the E field vector? What is the magnitude and the direction of the electrostatic field at that point, due to the presence of this pair of point charges? The point charges that are creating the field are known as source charges. Whatever's creating a field is known as a source charge. And the location P, where we're measuring the field, I usually refer to as the point of interest or the location of interest. Often textbooks and websites will refer to that point P as a field point. Now, what is this all about? I mean, first of all, let me make clear that whatever the field is, and I'm going to try to explain field in a moment. I mean, we just started talking about it last week, but whatever the field is something that exists everywhere. There's no particular point in space that has field any more or less. There's field everywhere in space. There's nothing special about that location 0, 0. The location 0, 0 just happens to be the place that we happen to choose to investigate what is going on electrically, to investigate the magnitude and the vector, the magnitude and the direction of the electric field at that point. We could have picked any other point. In any other place, we would have a different answer, an arrow pointing in a different direction with a different length. So the point P is just the point that we are happening to investigate and compute the electrostatic field. That's the first thing I want to say. Now, second, what is the electrostatic field? What do I mean by it? Well, this is the thing that we actually try to arrive at or establish at the end of the class. Oh, there goes my board. Hang on one second. Come on. All right, I'm going to give it a second. I mean, it'll disappear and it's all on a delay. Okay, but write everything down quick. Okay, what the electric field is a net electrostatic force per charge. Force is something one object does to another object. Field is something one object does to space. Field is a function. It's a vector valued function. What field is a mapping. See, there goes the board. Well, I have to wait till it. All right, I'll put the board back up in a second. But field is a function The input for the function known as field is a point in space, specifically some displacement in space from an origin or some kind of zero. But the input into field is location in space, and the output for field is a vector with magnitude and direction, a vector that indicates force per unit charge, force waiting to happen. What do I mean by that? What do I mean by force per charge? What do I mean by force waiting to happen? What I mean is force necessarily, and again, I know the board is gone. I'm waiting for it to, well, it's on. Hold on a second. I'm sorry. The board is, hold on one second. Yes. Okay. Okay. So maybe read this sheet for the moment almost upside down. Like look at the equation first that has an F before it. Look at this equation. This equation that I just circled in red is the electrostatic force that one charge Q1 exerts on some other charge Q2, specifically one point charge Q1 will exert on some other point charge Q2. The idea is just like with masses and just like with gravity, if you have any one point charge over here somewhere in space, it will automatically and necessarily exert a force on any and every other point charge anywhere else in space. Each and every one bit of charge in the universe automatically pulls or pushes each and every other bit of charge in the universe, just like all masses automatically pull on each other throughout the universe. The gravitational force and the electrostatic force are known as fundamental forces because they kick in automatically. For a proton to pull on an electron, the proton doesn't have to do anything. The proton doesn't have to touch the electron. And the proton doesn't have to worry if anything is sitting in between or not sitting in between the proton and the electron. If there is a proton and if there is an electron, they automatically pull on each other with a certain number of newtons across empty space, no matter how much empty space there is, okay? And that's the same thing with bits of mass, automatically pull on each other through empty space. They pull on each other in a manner that is directly proportional to the size of each charge. That's what the Q1, Q2 in the numerator means. And they pull on each other in a manner that is inversely proportional to the square of the distance between the two charges. That's what the R squared in the denominator means, right? Everything before the QQ and the R, everything in the parentheses is a bunch of constants being multiplied together, which makes one big constant. So it doesn't change the concept of what I'm saying. It just adjusts the numbers so that we stay in MKS units. Okay, and the R vector, the R hat on the right side of the equation is there to indicate that this whole thing, once you multiply it together, produces a vector of a direction that points along the line of R. What is R? R is the displacement vector from one charge, from Q1 to Q2. So the R hat at the end doesn't have any magnitude. It doesn't change the numbers or anything. It's just saying that the direction of this entire force either points along or against the line that you could imagine in your mind connecting one charge to the other. Okay, that's a mouthful. That's a lot of details. The main thing I'm trying to say right now, but I mean, in principle, we said all that last week. The main thing I'm trying to say right now is that evidently this electrostatic force that is exerted by any one bit of charge in the universe onto any other bit of charge in the universe, evidently this force not only happens automatically through empty space, but apparently it depends on pieces of information, such as how far apart in space the two objects are. Now let's pause for a second and think about that conceptually. Before I go on with all this math, like I want you to think about this force conceptually for a moment so that you'll understand why we move our discussion to a discussion of fields and why all of our computations and our concerns till the end of the semester are about fields. The force, like all forces, is what one object exerts on the other. In this case, the objects are point charges. The force is what one point charge does to the other. The force is measured in newtons like any other force. The force is a pull or a push, an interaction between the two objects like any other force. But the catch is this. This force, like the gravitational force, acts through empty space without any touching or any activity or any physical contact of that kind. Yet, it depends on how much empty space there is between the two objects. Now, think about it. That's a little strange. And when I say a little strange, I'm totally exaggerating. It's actually enormously strange. Here's what I mean. I'm not saying it's impossible. Well, I'm not saying it's not true, and I'm not saying we can't make some sense of it, but it's very surprising, I think, other people have thought, that a proton over here pulls on an electron over here with an amount of newtons that depends on how far the electron is from the proton. That means if nothing else is going on, if you just have this proton and electron isolated in the lab or isolated in outer space or far away from other effects in outer space, if the proton starts pulling on the electron with a certain amount of newtons, the electron will come toward the proton, let's say, right? But then that means it'll be closer to the proton. So now that it's closer to the proton, the R between them, the distance between them will change. The R in the denominator of this equation will change. Therefore, the overall F will change. If and when the electron starts coming closer to the proton, the number of newtons with which the proton pulls the electron will start increasing. The closer the electron gets, the harder the proton will pull. Okay, so what's the big deal? Well, the big deal is this. We're saying that the closer the electron gets to the proton, the harder the proton pulls. But we're also saying that the proton's not touching the electron or grabbing it in any way. Or we're saying that the proton and the electron are separated in space, but the proton keeps adjusting its exertion based on how much empty space there is. We're saying that the proton pulls harder the closer the electron gets, which has to mean that the proton, in some inanimate but real way, knows how close the electron is, even though they're not touching. Let me say that again. If the proton pulls harder and harder on the electron as the electron gets closer and closer to the proton must be finding out how close the electron is to the proton. Now, I'm not trying to be weird. I'm not saying that the proton consciously knows. I'm not saying the proton is thinking about it. I'm not saying the proton has any feelings about the matter. I'm not saying that. But I'm saying if the proton is exerting a force that depends numerically, rigorously, precisely on the location of the electron relative to the proton, then that has to mean that the proton has access to, has the information of where the electron is. The closer the electron gets, the harder the proton pulls. So the proton is somehow receiving updates as to the location of the electron, right? I mean, I'm going to say it one last time and then I'm going to move on. But the proton pulls harder as the electron gets closer to it. So the proton has to have the information of how much closer the electron is. Otherwise, how is it changing its pull, right? And again, I'm not trying to be weird. I'm not saying it's an animate thing or a conscious thing or a human thing. I'm not saying that. But I am saying the information, the whereabouts, the address of the electron, if that is determining the pull exerted by the proton, then the address of the electron must be accessible to the proton somehow, scientifically. So the information of one charge in empty space must be somehow accessible to any and every other charge in empty space. Where is this information kept? How does this information get updated? Through what vehicle or medium does this information get transmitted between charges? We call the answer to all those questions the field, okay? The idea is that when a proton gets put in space, in a lab space, in outer space, wherever, somewhere in the universe, if we put a proton somewhere, what we believe or how we model this, how we organize these crazy phenomena in our minds is we say, okay, once the proton gets put down, the information appertaining to its size and its whereabouts gets deposited everywhere in space in the form of vectors. None of this is literal, please understand. But we're saying that the minute a proton is down, the fact that it is down somewhere, the size of it and where it is somehow sitting everywhere in space. And if an electron comes along, and that's somewhere, this bunch of vectors everywhere in space is called a field. And the minute an electron or some other charge gets deposited in space, it's really getting deposited in the field of this first charge. The charge that causes the field is called a source. And the charge that is deposited or finds itself in the field and receives a force from that field is called a test charge. It's called a test because the idea is that the field is there, whether or not the test charge is there. The idea, in other words, I'm going to say this one last time, and then I'm going to move on sort of with the math. But once upon a time, we might have said a proton pulls on an electron, or we might have said the sun pulls on the earth. But once we started realizing that this pull seemed to be happening through empty space, and that adjustments to this pull seem to be getting transmitted all the time through empty space, we had to start believing that the information was sitting there in empty space and getting updated in empty space all the time. The information must be everywhere and moving back and forth between these objects. Otherwise, the objects could not be adjusting their interactions to this. Again, I'm not saying any of this should be the way the universe works. I'm just saying this evidently is the way the universe works. I'm saying these equations describe how objects interact in the world. It's very strange that objects interact in the world without touching each other. It's very surprising. But if they do interact, but they seem to do it. So in other words, these equations get verified all the time predictively, like the gravitation equation, which has the exact same mathematical form as this, got verified among other times the minute we put a man on the moon. I mean, no joke. And every time we've correctly predicted an orbit of a planet or an eclipse of a moon, it verifies these larger equations. So what I'm saying is we used to say something like a proton pulls on an electron, a proton exerts a force on an electron. Now, instead, we say the proton creates an electrostatic field. If the electron is in the field exerts a force on the electron. What is the field? The field is all the information describing the original source, all the information in a bundle, in a vector, ready to be exerted on any charge that comes along to experience it. I'm going to flip back the page again in a moment and show you the picture again. But mathematically, the field is not a hard, conceptually, the field is kind of a strange concept. Conceptually, what I'm saying is I exert a force on you. I create a field on space. Field is what I do even before you come along. Field is me getting ready. Field is me creating a force that's waiting for you to come along and act. If you look back at this picture, and then I'm gonna do the calculation. But if you look at this picture, if you look at the blue charge Q1, the plus 5 Coulomb charge that's sitting there at coordinate 5,4, look at those red arrows that are coming out from it. Those are just a representative array of arrows, but a representative, set of vectors. They are a depiction of what we understand the field to be. The idea of the field is if you picked, due to that positive charge there, if you picked any point in space and asked what's going on at this point of space due to that one positive charge, you would see a little arrow you wouldn't literally, I'm not saying there's literally arrows in space, but you could imagine, you could represent a little arrow at whatever point you are, oriented, radiating out from the positive charge, pointing in a direction out from the positive source charge, and with a length that gets smaller and smaller as you get farther and farther away from the source charge. Hold on, someone's here. One second. Okay. The idea again is this, like that's a field. Like those red arrows are a bunch of vectors representing the field due to Q1. The field is you input some location in space, you pick some point, and the output is there's a little vector at that point whose direction is the direction in which a force would be exerted on you if you were a positive 1 Coulomb of test charge. If you put 1 positive Coulomb of charge right there at some location, then it would be shoved in the direction of the arrow that you find at that location, and it would be shoved by an amount that is constant times the original Q over R squared, over the square of the distance between you and the original charge. It would times that would be the total magnitude of that arrow sitting at whatever location you choose. The arrows are pointing out from Q1 because the field is a prediction, or the field is a statement of what would happen to each and every 1 Coulomb of positive charge that could ever be placed at a location, in the neighborhood of the original source charge. They're pointing out because positives always push, always repel on other positives. If I were to draw the red arrows created by Q2, the negative charge, like if I were to draw a similar picture over there at the Q2 point, I would draw a similar bunch of arrows that were all getting smaller and smaller as they radiate out from Q2, only they'd all be pointing in because Q2 is a negative charge. Negatives pull on positives, positives push on positives. And whatever field picture we draw, whatever field concept we're thinking of, it's always a prediction or a statement of what would happen to a positive test charge. That's what it is conceptually. The field is all the information of the force divided by whatever's receiving the force. Mathematically, what the field is force per charge. There goes the board again. If force is measured in newtons, then field is measured in newtons per Coulomb. If I say at a certain location, hold on, I'm just trying to get the board back. This will be faster this time because I've caught it in time, I think. Yeah. If I say that the field at a certain location is 70 newtons per Coulomb, pointing that way, it means that for every 1 Coulomb of positive charge that might find itself at that location, it will experience a force of 70 newtons. If I put 2 Coulombs at that location, they'll together receive a total force of 140 newtons. Field is force per charge, therefore force is charge times field. So the math is not the math of what field is. Hello. That's nobody needs to see that. Wait. Oh my God. Okay. Right. So if you just look at the two equations, I mean, and you might you might still be intimidated by that whole big constant in the parentheses before the Q over the R squared. It's just a constant. It just has a numerical value that you don't have to memorize, but is always the same. Okay. Don't be intimidated by all of that. We write it in a funny way for reasons I will eventually explain, but that's just the stuff in the parentheses is one big constant. The R with the caret over it just means unit vector. It doesn't have any it has magnitude of 1. It doesn't change your numbers. It just means that the whole vector points along the line connecting one charge to the final location or to the other charge. So don't get bogged down. Don't get intimidated by all those symbols. The main thing to look at is that F is Q times Q over R squared. And E is just Q over R squared. In other words, E, if you look up here, E is just F over Q. It's the amount of force that would be exerted on each one unit of positive charge. It's a way of saying the field is all the information of the force bundled together, waiting to happen. It doesn't become a force until there's a second object at that location. But bottom line, again, I'm going to say it, and then we're going to do the math. Let me look at the time. Yeah, then we're going to do the math. Force is something I do to you. Field is something I do to locations in space. The field is the information of the force waiting to happen, waiting for a second charge to come along and receive that information and thereby make it or experience it as an actual force. Okay. You can, I mean, force is measured in newtons. Field is measured in newtons per coulomb. Now, the reason we have a math problem to do here, though, is what we're saying in the problem. We've got these two charges in the universe, in this case. Each one is creating its own contribution to the field. Like the Q1 is pushing out any little proton or any little one positive charge that could be anywhere in its neighborhood will be pushed out by it in a certain direction and with a certain number of newtons. But then there's this other charge that's pulling in toward it, right? So they're each a source. They're each a point source that's contributing to an overall space that's ready to shove electrons or protons around in some way. What we want to know is at some chosen location, such as the origin of this coordinate system at this location 0, 0, we want to know, well, what would happen? We want to know the field at 0, 0, what that really means after all of what I just said. Well, we're really trying, when we say we're going to solve for the electric field vector, the electrostatic field vector at 0, 0, we're really asking, is if we were to place or find 1 positive coulomb of charge, 1 coulomb of positive charge at 0, 0. What we really want to know is in what direction would it be pushed or pulled, and with how many newtons of force. We want to know how many newtons of force would act and in what direction on each and every 1 coulomb of charge that could possibly ever be found at 0, 0. We're asking for the force per charge waiting to happen at 0, 0. So we're asking for a vector. We're asking for an arrow whose direction would be the direction of push or pull that would instantaneously occur, and whose length would be the number of newtons per each 1 coulomb that would happen. Okay. Well, so we're really trying to find a vector which will be the sum of the 2 vectors each contributed by these 2 source charges. Okay, if you look at this crowded picture, you might notice if you stare at 0, 0, you'll see there's 2 arrows coming out from it. Like what are the 2 brown thin arrows coming out from it? What are they? Well, the arrow that's pointing down and to the left is a representation of the field contribution made by Q1. Like Q1 is positive and it's up there, like above the origin and to the right of the origin. So, but it's positive, right? So it's pushing out like all those red arrows seem to indicate. So I'm saying if we were to look at 0, 0, if we were to put 1 coulomb of positive charge at 0, 0, we would be pushed out. We'd be pushed by the Q1. We'd be pushed along the line, like in other words, this line the line from Q1 to point P, that line, the displacement from Q1 to the origin, that displacement is called the R vector. R is the displacement pointing from Q1 to the origin. Well, the point of the equation, of the electrostatic force equation, is that the field must point along that direction. If the charge causing it were negative, then the field would point against that direction. But it's got to be either parallel or anti-parallel to it. So the brown arrow is saying, yes, if I'm at 0, 0, I'm going to be pushed down and to the left, like along the line of R. I'm being pushed because the source charge is positive. I'm being really repetitive here. So I'm being pushed with some amount down there. But then there's this other charge, Q2, and the other charge, Q2, is negative. So it's pulling. So there's some arrow pointing from the origin to Q2, call that displacement R2 if you like. I'm saying the total thing that's happening at 0, 0 is it's being pushed down and to the left by Q1 while it's simultaneously being pulled up and to the right by Q2. So those two, and the Q2, so it's 2 vectors. And my whole job here is to add them together, to add together these field contribution vectors. So if you follow, so everything I just said now, for good or for bad, everything I've been saying for the last 20 minutes is about the concept of field and what it means and how to picture the significance of a field vector. But ultimately, what I've now, if any of that made any sense, what I've now done is drawn the 2 contributing field vectors that I think are occurring at 0, 0, 2 field vectors because of the 2 charges that are causing them. Our whole job now is just to add those vectors together in the same way that we added displacement vectors together in Physics 203, or velocity vectors or force vectors. We're just going to add 2 vectors together. I mean, it's not a short computation, but it is a procedure we've done many times before. So I'm going to add these 2 vectors, E1 and E2. So if you look at the bottom of this page, first of all, just to picture it, I'm going to add them. Sorry. Okay, so here's E1, here's E2. And so I'm placed, so to add them, or to picture me adding them, I'm placing them tip to tail, forming 2 sides of a triangle. And I'm saying the missing side of that triangle, the final vector that points from the original tail to the last tip, that is the answer I'm looking for. The answer I'm looking for will, if my diagram is at all correct, and it's obviously very, very rough and not to scale, but if it has any accuracy to it at all, my final answer should point down and to the left somehow. So we'll see. But that final vector is what we're looking for. Look at what we're looking to solve for. I'm just looking at the time. Okay, we've got a half hour. Okay, so that's what we're trying to get. The final E vector, that is the sum of E1 and E2. How are we going to do this? Well, we're going to add these 2 vectors by the component method, just like we did in Physics 203. So let me just remind you, for one thing, what I mean by components, if you've got, this is like a GDP here, an in general thing. In general, in general, if you've got some vector v and it points in some random direction as measured from the horizontal, like the adjacent component to, SOHCAHTOA means the cosine is equal to adjacent over hypotenuse and sine is equal to opposite over hypotenuse. Any random vector can be viewed as the hypotenuse of some right triangle whose legs are the components of that vector pointing along the constituent Cartesian axes. So like if some random vector v, the adjacent component, the extent to which v points along the x-axis is v cosine theta, and the extent to which v points along the y-axis is v sine theta, right? I'm just reminding you that, v being any vector at all. I'm just reminding you that from Physics 203. So if we look at E1, that vector that points from Q1 all the way down to the origin, that vector is known as E1. It pointed from the point 5,4 down to the point 0,0. So that angle theta, right? That angle theta as measured from the horizontal, I don't know what the angle is off the top of my head, but I know that the cosine of it must be adjacent over hypotenuse. I don't even need these negative signs are probably just confusing for the moment. Right, so the cosine of that angle is the adjacent 5 over the hypotenuse, which would be the square root of 5 squared plus 4 squared. In fact, right? Okay. So let's calculate. I want to calculate what I'm going to do here to do component method. I want to calculate the x component of the first field contribution, and I want to calculate the y component of it. Then I want to calculate the x component of the second field vector contribution, and I want to calculate its y component. I want to add the x components together. I want to add the y components together. I'll get one big x component, one big y component. I'll make one big right triangle out of those big x and y's. And I'll Pythagorize, like the answer to my final answer for the magnitude of the resulting field will be the length of the hypotenuse of that big triangle, and the direction of the field will be the angle theta formed between the hypotenuse and the horizontal leg. That's my method. I'll add that. 1 second. Okay, so this is the method we're doing. I think this is what it's, and I'm going to do it now. And again, I know we have 25 minutes. So we're going to take each. So this method that I just wrote here, and stop me if you can't read any of the handwriting, but this is the general method, again, that we did. This works for any kind of quantities that are vector quantities. We're now here we're applying to field vectors. So we're going to get the x component of field number 1 and the y component of field number 2. We're going to get the x component of field number 2 and the y component of field number 2. I just said that wrong, but you know what I mean. And then we're going to add together the x's and get one big x. And we're going to add together the y's and get one big y. We're going to form one big triangle from that. And the hypotenuse of that one big triangle is the magnitude of our answer. And the angle between the hypotenuse and, say, the horizontal leg will be the direction of our final answer. Our final answer will be a vector representing field. It will have magnitude and direction. It will mean the number of newtons that will, and in what direction will force be exerted on each and every 1 coulomb of positive charge that we could imagine finding at the origin. We're going to do the calculation now, but again, one last thing. Why do I keep saying on each and every 1 charge that we could imagine at the origin? Because the whole point is, if there actually were charges at the origin, then we'd already have a force, and then we're just talking about force. We're talking about field here, which is the force waiting to happen. Field is all the force information exerted by the source, but independent of whether the test ever is there to receive the force or not. Force is what I do to you. Field is what I just do to space. Field is the force waiting to happen. Again, force is measured in newtons. Field is measured in newtons per coulomb. So the field is what would happen to every 1 coulomb of charge positive that might be at a spot. But it's not assuming that there is charge at that spot. The field is just there waiting for the charge to come along and experience it. And it's there even if the charge never comes along and experiences it. Okay, so this is what we're going to do. And I know we're starting to, okay, so here we go. Okay. So let's take field contribution 1, the x component. Okay, I'm plugging it. The equation I'm plugging into, I'll write it again at the bottom. I'm plugging into this. Everything I'm doing here is plugging into this. Like I'm just getting magnitudes here, okay? And that complicated looking thing in parentheses is just one big constant, which is approximately 9 times 10 to the 9th Newton meter squared per coulomb squared. Okay, you don't have to memorize it. Oh, yeah. Oh, okay. All right. That's great. There's a great question about the, wow, you're way ahead of me. Okay. There's a great question about like 2 steps down. I totally see your question about the 3/2. Great question. I'm going to answer that. Let me just, that means good. I'm going too slow, apparently. Okay, let me just do the first 2 lines and I'll get to that. But great question. So I'm plugging into this equation down at the bottom. Again, the parentheses is just that constant, 9 times 10 to the 9th. So then I put in for Q, the charge 5. Please notice I'm not putting plus signs or minus signs or anything into this. I'm just doing magnitudes right now. Right, and the signs I'll worry about at the end. So the charge is 5, Q is 5, it goes in the top. R squared is the square of the square root of 4 squared plus 5 squared, right? Like R squared is, R is that hypotenuse that we drew. I'm almost about to answer that question that was just asked, but right, the hypotenuse is a square root of 5 squared plus 4 squared. So that whole thing squared is R squared. So we get Q over R squared is 5 over 4 squared plus 5 squared. But then multiplied by the cosine of the angle. The cosine is adjacent, which is 5, over the hypotenuse, which is square root of 4 squared plus 5 squared, right? So then if you go to the next line, now here, I want you to know here, I'm just rounding. I often will do this, just like we often round 9.8 meters per second squared to 10. Often I round 9 times 10 to the 9th to 1 times 10 to the 10th, just because it makes all the math like a lot easier to see. And we're just getting approximate values. So, okay, so that's all I'm doing there is I'm just approximating. Okay. But then now the question in the direct chat, like 5 over 4 squared plus 5 squared, well, that's 5 over 41 times 5 over square root of 41. So what that now, to answer the question that was in the direct chat, that means it's 5 squared over 41 to the 3/2 power. Like that 3/2 is modifying the root. I don't mean 3/2 times 41. I mean 41 to the 3/2 power. Like I could write it like this. And I'm just writing that because you'll often see it this way on the web sites or in textbooks. I'm saying 41 times the square root of 41 is like 41 to the first power times 41 to the 1/2 power, right? So it's, if you add them, so you add the exponents together and you get 41 to the 3/2 power. In other words, the square root of 41 to the third. If you don't like that, don't worry about it. It's another way that some of you might put it in your calculator to make it easier. And direct chat person who asked me, please let me know if I am answering the question or not. The 3/2, I'm saying it's 41 to the 3/2 power. And this pattern, it comes up so frequently in problems like this that it's just worth noting. You'll see it in textbooks like that. But please, oh, yeah. Oh, okay, great. Okay, cool. Okay, so thank you. Awesome. Okay. So we have 1 times 10 to the 10th times 25 over 41 to the 3/2 power. So I'm just doing it out, 41 to the 3/2 power, which again means really 41 times 41 times 41, square rooted. That's what that means. On your calculator is like 263. So I'm just like, calculating this all out. And finally, I get 9.5 times 10 to the 8th newtons per coulomb for the X component of the first field contribution, from the first charge, Q1. But look at my picture. If you look at my picture, that first field is pointing down and to the left. If you look at the horizontal component of it, it's pointing to the left. Now, that 5 is just displacement, right? That 5 is not like the answer that I just got, but look at the direction of the arrow. It's pointing to the left. And if we're all saying that on this axis, up is positive and down is negative, and on this axis, right is positive and left is negative, which I think we said on the previous page, then this whole field contribution, the horizontal component of the first field contribution is negative. I'm just saying, well, here it's negative 9.5, approximately 9.50 times 10 to the 8 newtons per coulomb. Again, that means that if positive 1 coulomb, if 1 coulomb of positive charge were placed at 0, 0, and nothing else were going on, it would be pushed to the left with a force of 9.50 times 10 to the 8th newtons. If 2 coulombs were placed there, they'd be pushed with a total force of like 19 19 times 10 to the 8th newtons, for whatever that's worth. All right, so that's my X component of field 1. What do I do next? Well, I go to the next page, and now I get the Y component of field 1. I do the exact same math, same equation, same equation again, but now I'm just doing the sine component instead of the cosine component. So it's that same equation again. Hello. Oh my God. I hope it's not safe. I'm saying now we're doing the y component. So it's that constant times q over r squared times the sine of the angle. And sine of the angle now is adjacent over is opposite over hypotenuse. Right? So now everything is the same as before, only in the numerator we have a 4 instead of a 5 because we're doing the other leg now. Okay, so it's the same, right? Hopefully that's clear. So same calculation, I've just changed from adjacent to opposite. So I've changed from 5 to 4 in the numerator. So that changes the number from 16 to 20. So I do out the math, and now we get like 7.60 times 10 to the 8th as a magnitude. But again, I'm saying negative. Why am I saying negative? Because look at that picture. The arrow is pointing to the left and down. Why is it pointing to the left and down? Because it's a push, because the point is up here over here at 5,4, and we're looking at its effect on the point 0, 0. So it's pushing, it's repelling down and to the left. So both of these components are negative answers. Okay, so now I put those in one side of my brain, and we've got 13 minutes left. We'll be fine. Let's take a break. No, okay, so we got 13 minutes left. So now we go to the other field contribution, E2, the field contribution from charge number 2. Now, this charge number 2 is also here in quadrant 1, but it's a negative source. Sources, things that create fields, can be positive or negative. But whatever the field is, it's always an investigation or a statement of what is going to happen to a positive receiver, a positive test charge. That's always the assumption. It's an agreement we're all making with ourselves that when we write down the field, we're writing down what would happen, what kind of force would be exerted on a positive test charge. Therefore, a negative source pulls, right? There's a bunch of electrons over here at coordinates 10, 3. So what's their impact on anything that might happen at the origin of this coordinate system? They would pull it up and to the right. So this vector is pointing up and to the right, right? And I don't know, right? And I have to figure out its components. Okay, so what do? I plug into that same equation. E equals constant times Q over R squared times cosine of theta. Okay, so I'm just plugging in here again. 1 times 10 to the 10th is the constant. So I'm on the first line. I'm here. The Q in the numerator is now 2, right? Because we're talking about Q2 now. So the magnitude of its charge is 2. Now I'm going to pause for a second. Stay with me. The charge is 2. Now the source charge, capital Q, is 2. If you're really paying attention, if you're really with me, you might be half consciously thinking, hang on, shouldn't it be negative 2? If you're thinking anything like that at all, or if you even see why I'm saying that some people might think it's negative 2, you're with me. If you see, like, right, because the given original charge, Q2, is a negative. Why didn't I put the negative in my calculation? It's not because I forgot. It's because I'm only looking at magnitudes here. And the negative, I've already taken into account when I said the thing is pulling. When I drew my diagram, I took into account that negative and said this thing is pulling, not pushing. And I'm going to use that diagram. I'm going to use the tips and tails to determine negatives and positives. So we're very much in vector land here, just like in Physics 203. All your vector diagrams really have to have tips and tails to indicate direction, which is the whole point of vectors, is direction. So it's my vectors that are doing the directional work for me. So I don't want to double count myself. So there's no more negative in that 2. I hope that's clear, or stop me in the chat if that's not clear. But I'm just calculating out magnitudes here and then putting on negative signs where the arrows tell me to. Okay, so I got a 2 up in the numerator, and then over 10 squared plus 3 squared. Okay, and then times the cosine of the angle. The adjacent is 10 over the hypotenuse is square root of 10 squared plus 3 squared. So you see the same pattern is happening as before. We get 20 in the top in the numerator over 109, in other words, 100 plus 9, right? 109 to the 3/2 power. This was the thing that direct chat person asked, a few minutes ago, but it like always happens this way because it's r squared times r, so to speak. Yeah, it's r squared times r. I mean, you know what I'm saying. It's r squared times r, so that's r cubed. But what is r? R is the square root of x and y. You know what I'm saying. So it's 20 over 109 to the 3/2 power. Maybe that's a bad way to write that. Maybe that's part of why someone asked. I mean, it was a great question either way, but so I'm trying to say like that. Okay. So if you do that out on a calculator, you get 1,138 and it's 20 to the top. So I did out the math. So now I'm like here at this line. Well, hello. So I'm here at this line. And so then I write it out in scientific notation and I get that E2x equals positive 1.76. Equals, I'm sorry, 1.76 times 10 to the 8th newtons per coulomb. But then I make it positive. Why? Because I look at my picture. I'm looking at that horizontal leg, the horizontal component of the E field is pushing, is pulling to the right. Right is positive. So it's positive. Then I do the same thing for the Y component. We're almost done, believe it or not, 8 minutes. I do the same thing for the Y component. Same math, only now, and now this confused people in the other, instead of 2 times 10, here, I guess I skipped a step. What I'm really saying here is instead of 2 times 10, I'm saying 2 times 3, right? Because 3 is the Y component. And that's the only change I'm making in the whole thing, just like I did before. So, so I do out the math, and now, I get a number, 5.27 times 10 to the 7. It's a much smaller number. Did I make a mistake? I don't think I made a mistake, because if you look at this picture, the Y component is a lot smaller than the X component, because this is a very slivery type of triangle. And 10 is a lot bigger than 3. It basically comes down to that. So I get that the Y component of the second field contribution is 5.27 times 10 to the 7th. Okay, now we're almost done. Now I have 4 pieces of information. I have the X and Y component of field contribution number 1 and field contribution number 2. What do? I'm going to add all the X. I'm going to add the 2 X's together. I'm going to add the 2 Y's together. I'm literally going to add. I'm going to add them because what the whole problem is asking is what's the total effect? What's the superposition of this push plus that pull? Now, the fact that one is a pull means, and one's a push means there's going to be minus signs involved, but I've already, wait, who is that? One second, I think that's for the other clip. Ooh, okay, that's a little late. Like minus signs and plus signs have already been tracked in my components. So I don't want to double psych myself. I'm literally going to add together these 2 sets of components, but wherever there's minus signs, I will include that in the addition. In other words, here we go. I make a chart, an X, and the board's going to disappear again, of course. But I'm going to make an XY chart just like we used to with displacements and velocities. And we would finish on time if my board wouldn't. What's going on? Come on, come on. The board is frozen, as you see. Give me 1 second, we're coming back. Okay. What? Okay. So okay. So I make an XY chart, and I know we have 5 minutes. Okay. So there's an XY chart at the top here, just like we used to do in Physics 203. We're adding together the X components from 1 and 2. We're adding together the Y components from 1 and 2. We're literally adding them because we're asking what's the total accumulated effect of both of these vectors working together. But indeed, some of the vectors are going one way and some are going the other way. So there's minus signs on some of them. There's minus signs on the two components from E1. There's plus signs on the two from E2. Okay. So when you add them together, you get negative 7.74 times 10 to the 8th. In the X, you get negative 7.707 times 10 to the 8th in the Y. So what do you do with that? You make one big triangle. You say at the end of the day, the field is pushing very heavily this way to the left, like with 7.74 times 10 to the 8th newtons on every coulomb that might be found there. And it's also pushing down or south or whatever on every, with 7.07 times 10 to the 8th newtons on every coulomb that might be found there. Where's there? At the origin, 0, 0, the whole point that we're calculating field for. By the way, the field is everywhere. Like I think I mentioned before, there's field everywhere due to these two guys. We could have picked any location in space and asked what the field would be there, and we would get some vector. It wouldn't be the same as this vector. The field, that's what the point of the picture of the red arrows was. There's field. Every point in space has one vector pointing in a particular direction. The array of all of these vectors everywhere in space, we call the field. The field is this forest of vectors that results from charges being in space. So, but this particular field vector at this particular location, we get the magnitude of it is the Pythagorean sum of 7.74 times 10 to the 8th squared plus 7.07 times 10 to the 8th squared, all square rooted. So we get approximately 10 or 1.05 times 10 to the 9th. In other words, we get like 10 times 10 to the 8th, but then we make it into scientific notation. So we get like 1.05 times 10 to the 9th newtons per coulomb. But these are very strong forces, very strong fields. Two reasons. One, and it's not wrong. Number one, the electrostatic force is very, very strong compared to, say, the gravitational force. But number two, I'm using numbers like 2 coulombs and 5 coulombs. That's actually a lot of charge. Those are big values of charge. So they are exerting strong forces. Again, that we're talking like quintillions and quintillions of protons and electrons here. But so the magnitude of the whole field that you get is approximately 1.05 times 10 to the 9th newtons per coulomb. And the angle, the direction in which this field is pointing, well, look at the picture. It's pointing down and to the left, as my original sketch sort of predicted or indicated. It's pushing down and to the left because the push from the proton is ultimately stronger than the pull. The push of the 5 coulombs is ultimately dominating over the pull of the 2 electrons, right? So we're ultimately getting more of a push than a pull here. So the ultimate effect, the net effect, the superposition, is that if you were to put 1 coulomb of positive charge at the origin, 0, 0, you'd get shoved down and to the left at an angle, or south and west, at an angle of approximately 42 degrees below the horizontal, 42 degrees southwest. Where did I get 42? I did the arctan of the opposite over the adjacent, right? Like of 7.07 over 7.74. The 10 to the 8th cancels out. So our final answer, the final field vector, is approximately 1.05 times 10 to the 9th newtons per coulomb in a 42 degree southwest direction. That is the field produced by 2 point charges. And that's a lot for today. So thank you as always for being so patient and understanding and flexible. And I will treat you the same way. Believe me that you are treating me. So thank you. And I'll hang out for a second if there's any questions, but I do have to go to another Zoom class now. So, okay, yes, have a nice day. Thank you. Okay,
Yeah, Professor, thank you.
Thank you very much. Awesome.
Have a good day, Professor.
You too. Yes, thank you very much. Thank you, Alex. Okay, great. Goodbye.